Hi everyone, I am Robin Reyes. Today, I will be discussing this research paper on the practical automation of excavators. The title of the paper is Practical Full Automation of Excavation and Loading for Hydraulic Excavators in Indoor Environments. It was authored by Hiroshi Yoshida, Tatsuya Yoshimoto, Daiki Umino, and Naoki Mori from the University of Tokyo, and published in 2021 through IEEE. As you can see on the table of contents slide, the paper is organized into 9 main sections. It begins with an introduction that outlines the background, reason for selection, problem statement, and objectives. This is followed by sections on methods, system architecture, experiments, and analysis of results. It'll then cover limitations, future research, and contributions. Along the way, I'll highlight the key aspects of each section. This paper explores the creation of an autonomous operation system for hydraulic excavators aimed at completely automating excavation and loading tasks within indoor environments. The construction industry confronts labor shortages and safety concerns, necessitating a shift toward automation to address these challenges effectively. Prior research has significantly progressed the automation of specific functions in hydraulic excavators. However, they predominantly concentrated on laboratory settings rather than achieving fully autonomous operation at actual construction sites. Most prior work looked at functions separately rather than a complete integrated system. In 2002, researchers worked on making a hydraulic excavator operate automatically using sensors and complex controls to guide its movements and route. In the late 2000s, studies were conducted on the forces affecting excavator buckets and using LiDAR and cameras to recognize the ground. This was done to understand operators' techniques in moving buckets, aiming to develop autonomous excavating machines. Moving into the 2010s, research has focused on automated functions like trajectory and path planning. More recent work in the late 2010s proposed techniques like adaptive digging using force and velocity. Other research explored various driving control techniques and analyzed force-torque trajectories across diverse soil types. Numerous research efforts have adopted control theory techniques like linear quadratic control to proficiently manage complex nonlinear dynamic systems. This overview of past research laid the groundwork, but full automation and practical testing was still lacking. This paper introduces an autonomous system developed to fully automate excavation and loading tasks performed by hydraulic excavators in indoor construction sites. The system uses a network of controls and sensors to guide the excavator's movements and overcome limitations in computer vision and hydraulics. Practical solutions are proposed, like delay compensation and an external actuator, showing how challenges of autonomous heavy equipment can be addressed. The researchers tested this system at an actual shield tunneling site to validate that full automation of excavation and loading is practically feasible with the right controls architecture. The authors aimed to develop a self-managing system that could automatically handle all excavation and loading tasks on a construction site. This addresses the issue of incomplete automation in previous research. Another objective was to test the practical implementation of the system at an actual shield tunneling construction site. This objective is essential as it moves beyond lab simulations to real-world validation. Real-world testing will show if the system can automatically do tasks on a job site as planned. The paper was chosen for its focus on creating an automated system for excavation and loading in construction using robotics. It highlights the significance of robots in construction, mentioning the development of autonomous machines equipped with sensors, controls, and machine learning capabilities. The authors emphasize the importance of testing robots on real construction sites to ensure their accuracy and efficiency, making their research significant for practical construction work with robots. This slide provides an overview of the various methods used in the research. Slope sensors and linear encoders were installed on the excavator to measure its posture and rotations continuously. A depth camera installed within the arm captured the volumes of soil in the bucket. 2D and 3D LiDAR were used for tasks like localization, terrain mapping, and truck detection. Inverse kinematics calculates the required joint angles for desired positions. Proportional integral control manages angle and position effectively, while also compensating for hydraulic delays. State predictive control prevented overshooting. Initiating movement involves parabolic path planning, guided position control, and travel enabled by friction compensation. Excavation and loading trajectories were defined through stochastic point selection and trajectory interpolation. A network of sensors gathers information wirelessly. An externally controlled actuator permitted operation from a remote location. This wide array of sensing, control, planning, and network system methods was vital to achieving the complete automation objectives. This slide provides a high-level overview of the autonomous operation system developed in this research. It gives a good sense of the system's key components and hierarchical control approach. This slide provides more details on the excavator and external actuator used in the system architecture. A standard hydraulic excavator already on site was used without any modifications, demonstrating the system's practical application. An actuator was installed in the cabin for remote control to safely operate the excavator without any changes to the machine. Sensors and encoders were placed on important parts of the excavator, like the boom, arm, bucket, and body, to track their position during automated tasks. This distributed sensing approach allows for highly accurate guidance and control without constant human oversight. The external actuator and sensor installation methods were, therefore, practical solutions for autonomous automation. A depth camera was installed within the arm to precisely measure soil volumes in the bucket, which is essential for tasks such as preventing overloading during the loading process. The camera captures RGB and depth images to differentiate between soil and empty space. The red and blue area in the color maps represent far and near area, respectively. The calculated soil volume is used to avoid overloading. A 2D LiDAR was installed to measure the excavator's position by detecting the center and slope of a white marker placed between its crawlers. This enabled the heavy machinery to be positioned and moved accurately, making the excavation process more precise and efficient. A 3D LiDAR unit is placed beneath the conveyor belt to capture a full view of the soil terrain in the soil pit. This created a map of the area to help plan where to excavate. The detailed terrain map helps adjust the excavation equipment accurately, reducing harm to its surroundings. A depth camera above the truck scale accurately measured truck parameters like position, size, and height through object detection. The sensors enabled the excavator to enhance its visual capabilities, allowing it to autonomously interact with soil piles and operate alongside dump trucks. The camera captures images in RGB and records depth information. In these images, Red areas represent far area and blue areas represent near area. This slide outlines the networked control system architecture implemented in the research. Sensors were connected wirelessly to mitigate installation challenges. This sensing method solves the problem of limited space in machines. A remote controller, situated at a distance from the excavator and trucks, significantly improved operational safety. Despite the introduction of delays by wireless communication, predictive controls were implemented to uphold precision. The network design integrated information from onboard excavator sensors with off-board perception of the environment and tasks. This facilitated a coordinated and hierarchical oversight over various interactive elements. Though subject to some limitations, the architecture demonstrated a practical solution for autonomous heavy machinery in real-world construction sites. By leveraging wireless technologies, it advanced previous research through a validated field application of distributed robotic and automated control. Posture is uniquely defined by bucket edge coordinates, X, Y, Phi. These are determined by boom, arm, bucket angles, θ1, θ2, θ3. Upper body rotation, represented by the angle θ4, is also a contributing factor. Inverse kinematics transforms XY phi to joint angles θi. Proportional integral control progressively adjusts each angle θi towards its target. Inverse kinematics is the process of calculating the angles of each joint, like the boom and arm, required to place the end effector, such as the excavator bucket, at a specific position and orientation. This is the inverse of forward kinematics, which determines the end effector's pose given the joint angles. By applying inverse kinematics, the system can autonomously maneuver the excavator one joint at a time to precisely achieve target bucket positions for tasks like digging. This allows for discrete step-by-step control of the hydraulic excavator's complex and non-linear movements. Inverse kinematics is a fundamental robotic and animation method that was leveraged here to enable precise human-level control of excavator postures during autonomous operations. The excavator's position on the worksite is defined using coordinate points, ST. The target positions for tasks like loading trucks are given using this coordinate system. A parabolic traveling path is planned between the excavator's current position and the target coordinates. This path allows smooth movement to any point on the worksite. The excavator's center velocity along this path is controlled proportionally to the distance remaining to the target. The speed and path curvature are used to determine the needed speeds of the left and right crawler tracks. A major challenge is overcoming the strong friction force between the crawlers and the ground, especially when starting to move. If the inputs exceed the static friction limit abruptly, it can cause errors in reaching the target position. To address this, a friction compensation control was developed. When initiating travel, it briefly elevates the lever inputs that deliver motion commands beyond the standard operating parameters. This allows static friction to be overcome smoothly and minimizes any position errors. Position control is mainly used for loading trucks at different locations and for correcting errors during excavating work. This ensures the excavator can reliably reach any position required to complete its automated work cycle. The excavation trajectory is defined by 5 factors: bucket edge angle to soil, upsilon, initial insertion depth, D initial, maximum depth, D max, dragging length, L, dragging angle, lambda. Upsilon is set vertical to soil slope at insertion. Lambda is average slope and dragging interval. D, initial, D, max, and L are calibrated through experiments. Trajectory converted to series of target bucket positions. X1, Y1, Phi1, X2, Y2, Phi2, etc. Excavator smoothly moves posture between targets, ensures appropriate amount of soil excavated, avoids getting stuck while digging efficiently. After excavating, bucket shaken to remove extra soil. This trajectory definition enables the automation of excavation operations to replicate the expertise of experienced operators. Calibrating parameters and the seamless posture control between targets enable efficient excavation while ensuring stability. The loading trajectory is defined by the start and end positions of the bucket edge. XS, YS, Phi S, XE, YE, Phi E. Positions are interpolated to gradually move the loading zone. Prevents overflow as weight in truck increases. Feedback from the truck scale reads the weight. When remaining weight below bucket estimate, the bucket opened little by little. Wiggle to adjust soil placement. Stops if target weight, 97% capacity, is exceeded. Ensures efficient yet safe loading. Shaping trajectory is also defined. The bucket edge moves horizontally along the truck bed rim. Forms stable soil pile within the truck bed. Prevents spillage during transport. This method enables automatic loading that precisely tracks weight and safely shapes the soil stack based on truck scale feedback. This slide summarizes some key results from the experiment and autonomous tests. A 5-minute and 23-second cycle shows that full automation is possible but can still be improved compared to human performance. Positioning errors during excavation corrections were less than 5 cm, indicating sufficient precision. The average weight loaded was 19.92 tons, close to the 20 tons target, with only 2 out of 14 trials having overloading. This demonstrated the system could achieve excavation and loading with high accuracy. The proposed autonomous system successfully completed real-world tasks efficiently and met essential criteria for accuracy and reliability. More analysis could further quantify the benefits and remaining challenges. This research had some important limitations. Testing was conducted only indoors under controlled conditions, without evaluating performance in varied outdoor environments. Only the tasks of excavation and loading were showcased, excluding other construction activities such as bulldozing. Coordinating multiple autonomous machines working together simultaneously was also beyond the scope of this study. While feasibility was shown, the autonomous system's 65% efficiency leaves room for improvement compared to human operators. Expanding outdoor testing and improving coordination between multiple machines are key steps to advance automation in real-world construction. To build upon this work, the presentation outlines several proposals for future studies. Conducting long-term outdoor testing in diverse conditions would evaluate the system's robustness over time. Adding more sensors may help in automatically measuring piles of soil. Creating a management system can make several excavators work safely together, making them more efficient than just one operator. Optimizing control systems could potentially boost the speed of movements. Using autonomous technology in different excavator models can make construction machinery more versatile and useful. Continuing this research agenda can help address the challenges raised and bring fuller automation to real-world heavy machinery applications. The study demonstrates that self-operated heavy machinery can effectively perform construction tasks, advancing the field of robotics. Using an automated digging and loading system at a real work site helps advance the technology in self-operating construction machinery. This field test shows that robotics and automation technologies can successfully execute complex industrial tasks in the real world. The study also highlights the remaining challenges to pushing the boundaries of robotics applications in heavy equipment and site operations. This work has significant implications for the construction industry. Robotics can help with the labor shortage in construction by automating tasks such as digging and loading. The research helps develop autonomous systems, making construction more efficient, safer, and better for workers through robotics and AI. This contributes to making the industry more efficient and sustainable through increased use of automation technologies. Thank you for your attention, and I'm happy to answer any questions through my email shown below.